Hey, good morning, everybody. I hope you've been having a great time in Singapore. My name is Bashar Alhafni, and I'm a PhD student at NYU, and it's truly a pleasure of mine to present our work on advancements in Arabic grammatical error detection and correction and empirical investigation. This is joint work with my colleagues Inoue, Khairallah, and Nizar Habash. So the task of grammatical error correction, or GEC, starts off by locating the errors in a given input text and then correcting these errors. The errors could be grammatical, lexical, and even involve punctuation. So GEC is a well-explored problem in English with many existing models, data sets, and shared tasks. And it's typically framed as a sequence-sequence problem with recent approaches relying on sequence labeling to basically improve efficiency. So we have models like Gector, Laser Tiger, and Seek2Edits. However, when it comes to morphologically rich languages, research on GEC has been limited due to data scarcity and language complexity. In this work, we focus on Arabic, which is a morphologically rich language, and we benchmark newly developed pre-trained sequence-sequence models on Arabic GEC. We introduce the task of multi-class Arabic grammatical error detection and investigate if using GED information within a GEC model improves GEC performance. We also explore using contextual morphological preprocessing and disambiguation in aiding Arabic GEC systems. So before I talk about the data sets and the models that we built, I'm going to present a brief overview on Arabic linguistic facts. So Arabic is a morphologically rich language that inflects for many things like gender, number, person, and case, and so on. There are about 22,400 possible part-of-speech tags in Arabic. Now compare this to only the 48 part-of-speech tags that exist in English. So given this morphological richness and in the context of GEC, you can imagine that you would have a very long tail of error distributions. Arabic is also diglossic, where we have Modern Standard Arabic, or MSA, as the formal form of the language that's standardized and typically used for news and informal settings. And we also have dialects that really vary based on where they're spoken in the Arab world, and they're mainly used in daily interactions and social media settings. Interestingly, native speakers frequently code switch within their own dialects and MSA when they write in MSA. And in this work, we focus only on MSA. Arabic also suffers from orthographic inconsistencies. So many Arabic datasets have frequent orthographic errors. For example, the alif hamza or the glottal stop and the ya letters. And to give you an example, this actually affects about 11% of all the words in the Pan-Arabic tree bank. Now, in terms of the data sets that we use, we start off with the Qalb 2014 shared task data that consists of about 21,000 comments that were written by Arabic native speakers. And the comments have an error rate of about 30%. And all of these comments were manually corrected. The second data set is the Qalb 2015 shared task that contains about 600 essays written by Arabic language learners, and the essays have an error rate of about 29%. And again, everything was also manually corrected. And lastly, we use the recently developed the Zeybak dataset that has about 200 essays written by first-year university students who are native speakers in the UAE. And this data set has an error rate of 24%. And again, everything was manually corrected. Now, starting off with grammatical error detection. So the task of GED really focuses on locating and identifying specific error types in a given text. But GED remains a challenge in Arabic due to the lack of manually annotated data. Now, in our work, we mitigate this problem by having a method that could automatically extract errors from existing parallel GEC datasets, and then annotating those errors based on error types using an automatic Arabic error annotation tool that is called Arita. So Arita models basically 7 error classes that cover orthography, morphology, syntax, semantics, punctuation, merges, and splits. So for instance, given a pair of erroneous and corrected sentences, the first step would be basically to align the words in these two sentences to extract the errors, and then pass this alignment to Arita to get the specific error types. In our work, we take advantage of the modularity of the Arita error typing to basically create different granularity of error typing. And specifically, we model 43 class grammatical error detection, or GED, 13 class GED, and then binary or 2 class GED. Now, in terms of modeling, we build word-level classifiers to identify the specific error types in a given text by fine-tuning Camel-BERT MSA, which is a BERT model that was pre-trained on MSA text. And for evaluation, we use precision, recall, and F0.5, and also accuracy. So F0.5 over here weighs the precision as twice as much as the recall, and it's a commonly used metric in grammatical error detection and correction. So for our results on the 3 data sets using the different GED granularity, we noticed an interesting pattern that whenever we model less classes, the numbers go higher in terms of F0.5, and this is unsurprising given that we are reducing the sparsity. However, interestingly, the error detection accuracy is kind of comparable across the 3 different granularity. And this really tells us that the models are struggling in identifying the specific error types rather than locating the actual error in the given text. Now, for grammatical error correction, we are interested in answering 2 main research questions. The first one is, does modeling GED explicitly improve GEC in Arabic? And the second one is, does morphological preprocessing improve GEC in Arabic? To answer the first question, we extend pre-trained sequence models so that they can become conditioned on the error types in the input. So given an Arabic sentence that has errors, which is X, and given a sequence of error types that are present of X, which is basically E, the goal of the model is to generate the corrected version of X that is Y. And in this work, we use 2 pre-trained sequence models, Arabart and RT5. To answer the second question, we make use of the recently developed contextual morphological analyzer and disambiguator to basically correct the erroneous input before passing it to the sequence models during training and inference. Now, for our baselines, we use basically 3 baselines. The first one is the morphological disambiguator I just mentioned, and we refer to this as morph. The second baseline is a very simple statistical lookup model that is based on maximum likelihood estimation. And the third one is ChatGPT. For evaluation, we use the max match M2 scorer, which is a commonly used metric in GEC that computes precision recall and F0.5 of the span level edits that are made by a particular model against the gold edits that exist in the reference. Now, in terms of our results on the development set, so starting off with the baselines, the MLE model claims the highest precision among all systems, but it does suffer from low recall. Interestingly, ChatGPT has the highest recall among the baselines for Qalb 2014 and Qalb 2015, but it does suffer from low precision. For the sequence models, RT5 and Arabart by themselves, so without morphological preprocessing or GED, basically outperform previous work on Qalb 2014 on Qalb 2015. And we notice that every time we include morphological preprocessing, GED information, or both, we observe consistent improvements across the 3 datasets. And on average, Arabart with morphology and GED was the best performing system, achieving 75.3 F0.5. Now, to study the effects of the GED granularity on the best performing system, which is Arabart plus morph plus GED, we train two additional models where we alter the GED system. And over here, we notice that the differing granularity GED models really behave differently in terms of recall and precision across the three development sets, with the 13 class GED being on average the best performing F0.5, achieving 75.4. We also estimate an upper bound of this by basically using gold GED tags instead of predicted GED tags. And we see that the most fine-grained GED tags, or the 43 class, really achieves the best performance across the three development set with an average of 80.2. So this really tells us that the reliability of the GED system in this model is really important. And the better the GED system is, the better the results. Now, on the test sets, basically, we observe consistent conclusions that GED always helps, and morphology does help sometimes, but not always. And on average, the Arabic model plus the 13 class GED was the best performer across the three test sets with a 76.1 F0.5. So to answer the questions that I posed earlier, so does modeling GED within GEC improve the GEC performance? The answer is yes, it does always. And does morphological preprocessing improve GEC in Arabic? And the answer is yes, sometimes. So in conclusion, we presented the first results on Arabic GEC by using recently developed pre-trained sequence models. And we introduced the task of multi-class grammatical error detection in Arabic. And we showed that modeling GED within GEC improves GEC results. And we also investigated the use of contextual morphological pre-processing and aiding GEC systems. And at the end, we achieved state-of-the-art results on two Arabic GEC shared tasks, datasets, and established a strong benchmark on a newly developed model. Our code, models, and paper publicly available. And thank you so much. And I'm happy to get any of your questions.
Thank you. Questions?
Thank you, Bashar. Sorry, I lost my voice, so apologies if I sound a bit funny. So yeah, thank you very much for the presentation. I have actually lots of questions, but I'll just ask one for the time being. So you mentioned for Arabic, we have like two limitations. One is data scarcity and also morphology. But since it's a sequence-to-sequence setup in the end, would you say morphology really matters?
So that's a very good question. So in my work on Arabic, I noticed that the less data you have, the more important morphology becomes. And it does provide that control in any sequence model task you have in Arabic. So I would say, yes, it does, based on the size of the data sets that you have.
Okay.
Thank you. Any more questions?
Hi, great talk. I wondered if you explored any of the options between 2 and 13 detectors, because if you think about the task, one of the kind of key things is, are you replacing a word, adding a word, or omitting a word, for example? So, just intuitively, detecting those three different options might help with the task of correction.
So basically, you're saying that for GED, just limit the GED labels to the basic edit operations you would actually basically have.
It's a hypothesis. I just wondered if you explored it.
Yeah, we have not explored that yet, but that's definitely a good suggestion.
Okay, thanks.
Thank you. Any more questions from the audience? I was also wondering, because you said that one of the main bottlenecks was the grammatical detection system, because it's obviously part of the pipeline.
Yep.
So what were the main struggles of this system, so to say?
So the main struggle, I would say, you mean in terms of the errors? So detecting the actual specific error types, because given the Arabic morphological richness, a single word could actually have up to 4 errors like morphology, orthography, and it could be really crazy. So the long tail of the error distribution, the GED model really suffers at detecting those specific types of errors.
So any specific type of error that it struggled with, or was it?
So I think when it comes to a lot of combinations of errors where you have, multiple orthographical and morphological errors in a single word, that's why when it really becomes challenging for the model.
Thank you. Great work. Let's
you.
thank the speaker again.
Thank you.